This problem here keeps Math Olympians up at night, and it is very simple in its statement. Does there exist a set of 5 distinct positive integers such that the sum of any 3 integers in the set is always prime? In any words, are there 5 magic numbers that make all 10 of these sums prime, and if so, how many such sets are there? Now there are a myriad of ways to solve this, but we're going to start by following the advice of the GOAT, Mr. Blue One Brown Blue One Brown Blue One Brown, and solve a simpler, related problem. Namely, to see if there is a set of 3 distinct integers such that the sum of any triplets of numbers is always prime. In this case, the only triplet that exists is just a plus b plus c, so we simply need 3 distinct numbers that sum up to a prime. Now this is a far easier task, and there are infinitely many solutions like 124 or 137 or 379 or 4811 and so on and so forth. Now you might be wondering why I've taken the time to give so many examples and list them in 2 separate columns. Well, that would be because we've just come across the first pattern of the video. All of our valid triplets must either have 2 or 0 even numbers. And this is a result stemming from one of the most basic properties of primes, namely that they're all odd numbers. Okay, fine, yes, 2 exists, it's prime and it's even, but the smallest possible triplet sum is 1 plus 2 plus 3, which is 6, so 2 alongside 3 and 5 may as well not exist for the purposes of our question. So anyway, for just 3 numbers, we've picked up 1 constraint on the parity of our numbers and infinitely many solutions. The natural next step is to try and build a valid set with 4 numbers. Now you could go back to the drawing board and just try and find a set of 4 numbers, and I'm sure you could with time, but it makes more sense to build on what we just did, i.e. to turn our sets of 3s into sets of 4s. So let's try this for 1, 2, 4, and we'll call the additional element x. This means that our triples are 1 plus 2 plus 4, 1 plus 2 plus x, 1 plus 4 plus x, and 2 plus 4 plus x. We already know that the first one is prime, but we need the other 3 to be prime as well. If we let our smallest sum up here be prime p, it means that the other 2 sums are going to be p plus 2 and p plus 3 respectively. But the keen-eyed among you will realise that not all of these numbers can be prime, because p and p plus 3 have opposite parities, so at least one of them is even and hence not a prime. And so that not only eliminates any set of 4 containing the numbers 1, 2, 4, but also any set containing 2 even numbers, which means that if our cool prime generating quadruplet exists, it must be all odd numbers. So if we lay out the workings in a similar way for the original triplet of 137, we end up with our 3 new triplets being p, p plus 4, and p plus 6. At this point, the easiest thing to do is just look up a fun little table of primes and look for 3 numbers that satisfy this pattern. And frankly, we are spoiled for choice. We could have 13, 17, 19, or 37, 41, 43, or 103, 107, 109, and so on and so forth. And for each of these solution sets, we could work out what the missing 4th number should be. Now this time we don't seem to have picked up any constraints. We do have 3 multiples of 3, but that's just how it panned out based on the numbers I chose. So with our 1.5 constraints, we can return to the original problem, looking for a set of 5 numbers such that every triplet sum is prime. We'll build on 1, 3, 7, 33, and again we'll introduce the 5th number as a variable. If we lay out all of the new triplet sums again, and call our smallest one 1 plus 3 plus y, p, we ultimately end up with p, p plus 4, p plus 6, p plus 30, p plus 32, and p plus 36. When I first reached this point, I thought it was highly unlikely that 6 primes would fall perfectly into this pattern of being 4, 2, 24, 2, and then 4 apart. But if we simply start going through the list, we do find some promising examples, and I've written the 4 of them under 400 here. But unfortunately, none of these supposed solutions actually work. These ones here circled in red are all composite numbers. Now, we should probably address the elephant in the room, the menacing column of failure and depression. Writing these numbers out as a product of their prime factors, we find one common culprit: 3. And unfortunately, this is Thanos levels of inevitable. If you want the first 3 terms to all be prime, then the 5th will always be divisible by 3. This is because the first number will always have to end in 3 or 7. If it ended in 5, 1, or 9, then one of the first 3 numbers would end in 5, so it would be divisible by 5. For sort of similar reasons, the first number will always end up being in the form 3n plus 1. Wait a minute. And what that means is that our 5th term, p plus 32, will end up being 3n plus 1 plus 32, which is 3n plus 33, which is 3n plus 11, and is thus divisible by 3. The more advanced way to explain this is by saying that p is always 1 mod 3, and since 32 is 2 mod 3, p plus 32 will be 0 mod 3, and being equal to 0 mod 3 is the same thing as being divisible by 3. So we've shown that with 1, 3, 7, 33, it's impossible to come up with a prime quintet. We could jump into another one of our quartets and see if it could work, or we could take a step back and finally do a little bit of generalization. The reason why our previous example just failed is because no matter what first prime we picked, hell, no matter what first number we picked, one of the other numbers would be divisible by 3. And we can explain this by looking at the value of these numbers here, which I'm going to call the shifters, are plus 4, plus 6, plus 30, plus 32, and plus 36, mod 3, which are going to turn them into 1, 0, 0, 2, and 0 respectively. This means that no matter the value of p mod 3, which if it's a prime number can only be 1 or 2, at least one term will end up being equal to 0 mod 3. Now where do these plus 4s, plus 6s, and so on and so forth come from? Well, these are all the pairwise sums of the numbers in the original quartet, and the mod 3 versions are the pairwise sums of the numbers mod 3 from the original quartet. If we look at all the examples we came up with initially, you might spot something interesting. None of these combinations have 3 of the same number when you consider them mod 3. And that's a necessity, because if we had 3 numbers with the same value mod 3, their sum would equal something that is 0 mod 3, i.e. a composite number. In fact, these are the only 6 viable sets of prime generating quartets mod 3. At this point, it's quite easy to verify by brute force that all of these sets generate a set of shifters that contain at least 1, plus 0, plus 1, and plus 2. Which means that no matter the value of the 5th element in the set, at least one of our triplets has to have a composite sum. So, just like that, the question is answered. There does not exist a set of 5 distinct positive integers such that the sum of any 3 of the integers is always prime. Now it's time for a quick little story. The title of this video, believe it or not, isn't technically clickbait. One of my friends sent this question to a slightly bigger group of friends, and they met up to try and solve it in like an hour, and they couldn't. But one of my friends, who when he was younger took part in the BMO round 1, which makes him a Math Olympian, couldn't just give up on the problem. So, and I quote, "Instead of going to sleep, I worked out the solution." And his solution is actually so beautiful and so simple, and we're going to speedrun it right now. Consider the 5 elements in the set. We know from before that we can't have 3 of them with the same value mod 3, otherwise that triplet will be a multiple of 3. So the only solution is that we have 2 with one value mod 3, 2 with another value mod 3, and 1 with the final value mod 3. This means that our set contains at least one number that is 0 mod 3, one that is 1 mod 3, and one that is 2 mod 3. These 3 numbers form a triplet whose sum is 0 mod 3, i.e. the sum is a multiple of 3, so not prime, so the 5 set doesn't exist. Yeah. So it turns out that it isn't really a difficult question, but this was definitely a video where I wanted to highlight the problem-solving process and how you could realistically find an answer instead of just jumping to the fastest solution. But for those of you who feel let down, I have got a challenge for you, and that is to consider the generalized case. For which values of m and n does there exist a set of m distinct positive integers such that the sum of every subset with size n is always prime? As a starter, I'll tell you that I think that n can't be 2 unless m is also 2, but I can't be bothered to prove that part. Anyway, that wraps it up for today. Like I said, this one was more about the journey than the final destination, but I hope you enjoyed it nevertheless, and thanks for watching.